Now we're going to start talking about sets. Sets are the most fundamental objects in mathematics. They are really, really elementary, and in a way, all of mathematics is constructed out of sets. So they are really at the foundation of mathematics. And very easy to work with and define. So this is a very nice chapter, very easy to learn. So set. I'm going to start by defining several notions. So let's start with the notion of a set. A set is just a collection of objects. That's it. There is nothing more to it. I'll give examples, all of them together later. Then an element is the object in the set. Okay, that's what an element is. Then you have cardinality. Cardinality is just the size of the set. Then the empty set is the empty collection. And a subset is a subcollection. Okay, so these are the terms that we need to understand in this chapter. Let's start with the first one. Set is a collection of objects. What is an example? So it's the collection of objects 1, 2, 3. Similarly, let's say T is the collection of all students at Weston. So I can form a collection of literally anything. That's what makes set theory so universal. I can create anything. Something that is very relevant to many of you, many of us today, is a notion from data science. A data set is just a collection of data points. What a data point precisely means depends on how the data is collected. But there's nothing more to data set. It's just a set in the mathematical sense. That's a set. Now an element is an object in the set. So we'll work with this example everywhere. And in that example, I'll say 1 is an element of S, okay? And it is mathematically denoted as 1, and then there's this weird symbol, which is like a C with a line through it. So this symbol stands for being an element. And if you want to say something is not an element, then you just put a line through it. So for example, I would say 4 is not an element of S. And this is the same way in which we say that when we say something is not equal to something else, we put a line through the equal sign. Same concept here. Okay, so that's how you write elements. Cardinality is the size of the set. And in this case, the size is the number of elements inside your set. So size of S, denoted like absolute value, will be 3. So that's it. Size stands for cardinality. Just 2 vertical lines in front of the set's name. Then we come to empty set, and this is easy to define, but it's something that many students get stuck at. It's just a definition, and the way math works is once you define something and it's useful, it doesn't matter if the definition sounds weird. As long as it's useful, we use it in math everywhere. So here, the empty set is the empty collection, and it literally is the empty set. There is no, so it's denoted like this. Curly braces with nothing inside. There's nothing in there. It's just empty. It's also written as phi. So that's O with a line through it, the Greek letter phi. It's called the empty set. There's no logic or rhyme or reason behind this. It's how it's defined. And it has nothing in it. It has 0 elements in it. So its size is 0. And both of these notations, either curly braces with nothing inside or phi, are used to denote the empty set. They're both very common. Finally, a subset is just a subcollection. So for example, you can say that 1, 2 is a subset of 1, 2, 3. Is just a subcollection. That's it. So this is denoted as follows. So subset symbol is C with a line underneath it. It's actually not a C. It's like a U, which is flipped 90 degrees. First remark about set. A set is just a collection. And so in math, the ordering of elements inside a set does not matter. That's the first thing. Second thing, just the way sets are defined, we don't allow repetition. So there's no repeated element. Both of these statements are true only for a set. There is a mathematical structure called a list, and in a list, the order does matter. Similarly, there is a mathematical structure called a multiset, and in a multiset, multiple elements, a same element can occur multiple times. Okay, so example, you can say like S, which was 1, 2, 3. Because the order does not matter, I could have written it as 2, 1, 3. I can write it as 3, 2, 1, and so on. I can also, because repeated elements are not allowed, I can just say that it's the same as 1, 2, 2, 3, because the repeated elements will just go away. But this is not preferred. Please don't repeat elements inside a set. I will just remove this. Okay, so these are the subtle points about sets. Cardinality is just the size of the set. It could be infinite. So for example, I can look at the set of all natural numbers, in which case I will get infinite, which is fine. Now we come to the subtle points about subsets. So a subset is itself a set. And in the above example, we saw that 1, 2, I'll call this S prime, is a subset of S, which was 1, 2, 3. And you can see that S prime is itself a set. Okay, and this is denoted S prime is a subset of S. Then second remark, an empty set is a subset of every set. That's another convention we use. Actually, you can derive it using logic, but it's a little complicated. So I'm not going to do that. Empty set is a subset of every set. What this will look like is that for any S, for any similarly I can say phi is a subset of S prime. Now before I come to my next remarks, let's do a problem about subsets. Question: list all the subsets of S. Where S was the set 1, 2, 3. Now the best way to list all the subsets is to do it systematically. The size of S is 3. A subset is a subcollection, so its size cannot be more than 3. So let's start with 3. The only subcollection of 1 to 3 of size 3 is the whole collection itself. So there is exactly one subset of size 3, that is 1, 2, 3. Subset of size 2, you can do 1, 2, 1, 3, or 2, 3. 2, 1 is the same as 1, 2. Similarly, 3, 1 is same as 1, 3, and 3, 2 is same as 2, 3. So there are no other subsets of size 2. Subsets of size 1 are 1, 2, and 3. And the last one, which many people forget, and you have to be very careful, the subset of size 0 is the empty set. Empty set is a subset of everything, so it is a subset of S. Okay, so we get total number. is 1 plus 3 plus 3 plus 1, which is 8. And if you look at 8 is nothing but 2 to the 3, and 3 is the size of S. Now, this is not an accident. This brings me to the next remark, which is in fact a theorem, or let's say a fact. The total number of subsets of a set S is 2 to the size of S. We'll prove this later in a chapter on combinatorics. Right now, you can just assume this statement to be true without proof. This, of course, only makes sense when S is a finite set. When it's infinite, this is not a valid statement. One last fact about subsets, and that is the notion of a proper subset. A subset which is not the total set is called a proper subset. So if you look at the above example, these subsets 1, 2, 1, 3, 2, 3, 1, 2, 3, and the empty set are all proper subsets. But this whole set itself is not a proper subset of itself. And there is a special notation for a proper subset. The notation is this. So I can write, for example, 1, 2 is a proper subset of 1, 2, 3. But to be honest, this notation is not commonly used. The preferred notation is the one with the U with an equal sign underneath it. But if you are required to find proper subsets, then you use this notation. Okay, so not a very important notion. Finally, there is a very mathematically succinct way of defining subsets. It's called the set builder notation. So say I want to create a set of all positive real numbers. Now notice that this is a subset of all real numbers. Here R stands for real numbers. So I'm asking you to take the set of all real numbers, and out of this, look at only the positive ones. So look at the subset of positive real numbers. And the way we create it mathematically is by something called set builder notation, which I'm going to describe now. So I'll just create a new variable x, and I'll say x is in R. This R is the same as this R here, and the same as real numbers here. Okay, so I'm picking some real numbers out of all real numbers. I'm picking positive ones out of all of them. That's why that R showed up. And this is, then we put 2 dots. These 2 dots are read as such that x is in R such that x is greater than 0. And this stands for positive. And we read this whole sentence as x is a real number such that x is greater than 0, or x is positive. So this is the set builder notation for positive real numbers. If I wanted positive integers, I can do it similarly as, let's say, s prime is x in z. Z is integers such that x is greater than 0, and this is the set of positive integers. Let's do something more interesting. Let's say I want to look at all the prime numbers between 1 and 10. So let's say T is the set of prime numbers less than 10. So I'll create this using a set builder notation as follows. We have to throw in a new variable, one that does not exist so far. So let's just say x. Then we have to ask, what is this a subset of? So I'm looking at prime numbers, and prime numbers are natural numbers. So I need n. Okay, n is the larger set that I'm focusing on, such that x is less than 10 and x is prime. So this is the set builder way of, this is the set builder notation of constructing this set. And I can actually write down what the elements are. I'm looking at elements which are less than 10, which are natural numbers. So 0, 1, 2, 3, 4, 5, 6. But then I'm picking only the ones that are prime. So I'll be picking 2, 3, 5, and 7. You pick a new variable, then you pick a large set S, such that some proposition on X is true. So that's the set builder notation, and these are the basics of sets.